Hi everybody, so in this video we're going to continue with Chapter 2, Functions, specifically Section 2.3, Zeros, Factors, and Remainders. So one of the first things that we have to become familiar with is certain terminology. So if we have that p of x is a polynomial function and c is a real number, then these statements are equivalent. X equals c is a zero of the function p. Okay, but that, of course, would only be if we have this polynomial and c is here. Then we can say that x equals c is a zero of the function p. X equals c is a solution or root. So we can also call this root or solution of the polynomial equation p of x equals 0. So obviously at p of x, or p of c, we should say, is equal to 0. That is because c would be a root or a zero of the polynomial equation or function. X minus c would be a linear factor of the polynomial p of x. That means that p of x would equal x minus c, obviously times other factors. And then c comma 0 is an x-intercept of the graph of the function p. We can see that c comma 0 is this coordinate here. If we call this coordinate here a comma 0, let's just call the point A, and then this would be B, then we could say that p of x would equal x minus a times x minus b times x minus c. Now this is supposing that this would be a degree 3 polynomial with 3 x-intercepts. Very well, so in the next slide we're going to find something about polynomial division, specifically example 2.11, and it says find the quotient q of x and the remainder r of x when p of x is equal to 2x cubed minus 5x squared plus 6x minus 3 is divided by d of x, x minus 2. So here what they want us to do is to perform something called long division. So we are going to divide 2x cubed minus 5x squared plus 6x minus 3. We are going to divide this by d of x, which is x minus 2. So how do we do this? Well, the algorithm for dividing polynomials is very similar to dividing numbers, right? For example, if we divide 17, say by 3, we know that we would say, well, 3 times 5 is 15. We subtract, we get 2. So this is what we call the remainder. This here is the quotient. Let's just call it Q for now. This is the quotient. And this is the divisor. So that's why they identify them as Q of x, D of x, and remember that the remainder, they said R of x, right? So now, of course, this is not a polynomial, but just for illustration, so we understand what we're going to do. So how do we divide these? Well, we would divide them just like we did with this example here that required finding a number that suits multiplying by 3 and getting close to 17. So you do something similar. You compare x minus 2, especially you look at the first term in x minus 2, and you ask yourself, okay, what can I multiply x to get 2x cubed? Now, something I forgot to mention is that you have to make sure that the polynomial is complete. What do I mean by that? Well, that all the terms are represented. So we have x cubed, x squared, x to the 1, and x to the 0. So that means that this polynomial is complete. If you were missing one of these terms, we would have to include 0 here in order to get an accurate result. So then, what can we multiply x minus 2 to get 2x cubed? Well, obviously 2x squared. So we write 2x squared and then multiply that by this expression. So we would get x times 2x squared would be 2x cubed, and then 2x squared times minus 2. So negative 2 times 2x squared would be negative 4x squared. And just like we do in normal division, we would subtract these terms. So obviously this is going to cancel out because 2x cubed minus 2x cubed is 0. But then we have to be careful here because this minus that we have in front of this expression changes all the signs in here. So this would be positive. Okay, so then it's going to be negative x squared. And then, just like we do in normal division, we bring this down. So plus 6x. So we bring down 6x, and we continue with the same algorithm. So the question would then be, what can I multiply x minus 2 times to get minus x squared? And that's obviously minus x. So we write here minus x, and then proceed to multiply. So we're going to get minus x squared plus 2x. And then again, we subtract. So this will eliminate, and this becomes a subtraction. So this will be then 4x. We bring down the last term, which is minus 3. So here we write minus 3, and then we ask the same question again. What can I multiply this here to get 4x? And that's going to be obviously positive 4. So plus 4, multiply it, and we're going to get 4x minus 8. Subtract the whole expression. This will cancel. This was positive. So we're going to get 5. And then we have everything we need. Why? Well, because this is the remainder. So this would be the r of x they were asking about. We have, well, we know that the divisor was this, right? This was the divisor. And we have the quotient. So this would be the quotient. Then what follows is to say that 2x cubed minus 5x squared plus 6x minus 3 is going to equal, just like here we'd say, well, 17 is equal to 5 times 3 plus 2, right? So we write quotient times divisor plus remainder. So we would say that this is the same as saying x minus 2 times what we got up here, the quotient. We got 2x squared minus x plus 4 plus the remainder. So in general, we can say that if p of x is a function and d of x is a divisor, q of x is a quotient, and r of x is a remainder, we can say that in general p of x is equal to d of x times q of x plus r of x. So what happens if we divide both sides by the divisor? Well, we would get that p of x divided by d of x is equal to q of x, the quotient, plus the remainder over the divisor. So next we're going to do example 2.12, and it says find the remainder when g of x is equal to 2x cubed plus 5x squared minus 8x plus 3 is divided by x plus 4. So something that is very useful here is something called the remainder theorem, which states that if a polynomial function p of x, as you can see here, is divided by x minus c, then the remainder is the value P of C. So what does that mean? That means that if we plug in C into the function, whatever result we get would be the remainder if we had divided by that factor. So in this case, it's x plus 4. But notice that x plus 4 is not in the form x minus c. So we have to be careful here. X plus 4 is the same as saying x minus 4. So that means that we have to test for negative 4. So we simply go g of minus 4 is going to equal 2 times negative 4 to the 3 plus 5 times negative 4 squared minus 8 times negative 4 plus 3. And this is going to give us 2 times negative 64 plus 5 times 16. And then we know that negative 8 times negative 4 is 32, so plus 32 and then plus 3. And then from here we're going to get negative 128 plus 80. And we can add those two. So this plus 35. And if you do the arithmetic, you're going to get negative 13. So then that means that negative 13 would be the remainder, commonly written as r of x. So this would be the remainder after dividing g of x by x plus 4. There is a corollary to the remainder theorem, known as the factor theorem. And what it says is that a polynomial function, p of x, has a factor x minus c if and only if p of c is equal to 0. So this is obvious, right? If we plug in, if we had plugged in negative 4 here, and g of negative 4 had given us 0, then x plus 4 would be a factor of g of x. That's just saying that it would be divisible by x plus 4. And that's obvious if you get a remainder of 0. So in the next slide, we're going to talk about the sum and product of the roots of any polynomial equation. So this is a very powerful theorem that can help us solve many problems, because it turns out that you know that you have a polynomial of degree n. So the first term is x to the n, as you can see here. So look at the notation. A sub n would be the coefficient of the first term. And then we would have the next coefficient as a sub n minus 1. The next exponent for x would be x to the n minus 1, and so forth until we get to x or to a sub 1, x to the 1, and the final term a sub 0. So notice that the theorem says that the sum of the roots is equal to, and this would be the second coefficient divided by the first coefficient with a negative sign in front. So it would be minus second coefficient divided by the first coefficient. And then we have, so this is the sum. And we have that the product of the roots is going to be negative 1 to the n. So that means that this n depends on the degree of the polynomial. This times the last term, which is a sub 0. So let's say the last term. And this divided by the first coefficient. So now we can use this to solve example 2.13. And it says 2 roots of the equation x cubed minus 3x squared plus kx plus 75 equals 0 are opposite in sign. So 2 roots are opposite in sign. Find the values of all the roots and the constant k. So this is a very typical IB exam problem. Okay, so let's name the roots, right? So let's call the roots in terms of alpha. Let's say that's the first root, but it says that two of them are opposite in sign. So we could have negative alpha as the other root, and let's call the third root beta. So those would be the roots. How do I know it has three roots? Well, that depends on the degree of the polynomial. So if you have degree 3, you are certain to have three roots. Now, not always real, but certainly you might have imaginary roots too, which is something we're going to see further down the road. But in this case, we're going to assume that we have three real roots. So we know that one root is alpha, one is negative alpha, and the other one is beta. So notice that we can find beta very easily using the theorem regarding the sum of the roots. So remember that the sum of the roots, in this case, if we say alpha plus negative alpha plus beta, should equal minus the second coefficient, so negative 3, and over this over the first coefficient, which in this case is 1. Okay, so notice that here alpha minus alpha just cancels out. So we have that beta is equal to 3. So we have one of the roots. Now we can solve for the other roots, alpha and negative alpha. We can use the other theorem, this one, that says that the product of the roots is equal to negative 1 to the power of the degree of the polynomial times the last coefficient, the last term, divided by the first coefficient. So that means that alpha times negative alpha times beta should equal minus 1 to the power of the degree of the polynomial, which is 3, times the last coefficient, which is 75, divided by the first coefficient, which is 1 again. So now we can say that alpha times negative alpha is negative alpha squared. But we know that beta is 3, which we got from here. So this times 3 is equal to, and this is going to give us negative 75. So we have that negative alpha is equal to negative 75 over 3. And then finally alpha squared, sorry. Finally we get that alpha squared is equal to 25. So that means that alpha is equal to plus minus 5. So we have all three solutions for the first part. We have the values of the roots. So the roots are going to be, let's put them in order. So negative 5, 3, and 5. Those would be the three roots. But they also want us to find the value of the constant k. So that's what we're going to do next. Very well. So we found the three roots, which were 3, 5, and negative 5. So now we have to solve and find constant k. So how can we do that? Well, if we know that these are the roots, right, we have 3, 5, and negative 5, then we know what are the factors. Because if these are the roots, then it means that the factors should be x minus 3, remember always opposite in sign, x minus 5, and x plus 5. And since we know that this is a degree 3 polynomial, there are no more roots to find. So if we multiply and expand this, we should be getting the original polynomial. So notice that this is the same as saying x minus 3 times x squared minus 25, because this is a difference. This is a difference of squares here. And then notice that we can say here that this is going to equal, if you multiply and expand everything, you're going to get x cubed minus 3x squared minus 25x plus 75. And
Notice that if we compare this to the original polynomial here, we have the same coefficients, right? We have 1 for the first coefficient, we have -3 for the second one, and then the last one is 75, the last term, 75. So that means that k has to equal -25. Okay, so now we are in example 2.14, which will be the last one on this video. And it says, consider the quartic equation 2x to the 4 plus 3x cubed minus 16x squared plus 15x minus 4 equals 0. Given that the equation has a double root of x equals 1, find the value of the other two roots. So we know that it has 4 roots because it is quartic, in other words, degree 4. So it has a double root of x equals 1, right? So that means it has 1, 1, and then 2 more roots that we're going to call x3 and x4. So let's use the fact that the sum of the roots, remember that the sum of the roots is negative second term divided by the first term. So that means that 1 plus 1 plus x3 plus x4 should be equal to -3 over 2, right? Second term coefficient divided by the first term's coefficient. And then from here, we're going to get that x3 plus x4 is going to equal -7/2. So I get the -7/2 because this is 2, and then if I subtract 2 from this, I'm going to get -7/2. Okay, then we also know that the product of the roots is equal to -1 to the n, which is the degree of the polynomial, times the last term divided by the coefficient of the first term. So that means, again, that 1 times 1 times x3 times x4 is going to equal -1 degree 4 times the last coefficient, which is -4, divided by the first, which is 2. And if we do the math here, we're going to get -4/2, which is -2, okay? And then, so this is equal to -2. So then that means that x3 times x4 is equal to -2. Okay, so we're ready to solve the problem using a system of equations, right? With 2 unknowns and 2 equations. Because we have that x3 plus x4 is equal to -7/2, and we also have that x3 times x4 is equal to -2. Notice that if we rearrange this equation here, we can get that x3 is equal to -x4 minus 7/2, and then we can use substitution. How so? Well, because this is x3, we're going to get that minus x4 minus 7/2 times x4 has to equal -2. Okay, then if we rearrange this, we're going to get that x4 squared plus 7/2 times x4 minus 2 is equal to 0. Okay, then from here, if we multiply everything by 2, we're going to get that 2x4 squared plus 7x4 minus 4 is equal to 0. Now this is easy to factorize because it's just going to be 2x4 minus 1 times x4 plus 4. So that means that we have two solutions for x4. So x4 can either be 1/2 or x4 can be -4. So what happens when x4 is equal to 1/2? So if x4 is equal to 1/2, then notice that we can just plug that into this equation, right here, and we're going to get that x3 should equal -7/2 minus 1/2, and this is going to give us -4. And then we have the other case. If x4 is equal to -4, you're going to get that x3 is equal to 1/2. So notice that basically it's giving us the same answers but backwards. That means that we have the other two roots. Okay. So the other two roots, or the other two zeros, would be, just to answer the question appropriately, the other two zeros would be 1/2 and -4.